The indirect utility function tells us for any set of prices and any income level how much utility the consumer will attain. The expenditure function, on the other hand, tells us for any set of prices and any utility level how much income is required for that consumer to be able to reach that utility level. It turns out that there's a clear relationship between the indirect utility function and the expenditure function, and we'll illustrate this here. Consider, for instance, the slice of an indirect utility function that holds prices fixed and simply shows the relationship between income and the maximum amount of utility that the person can get in utils. As income goes up, the utility goes up as well. We might, for instance, be using a particular ruler to measure utility such that an additional dollar in income causes utility to go up by 0.25. This would give us a slope of 0.25 for the slice of the indirect utility function that we've graphed here. The indirect utility function itself, of course, has a more complicated form. It's a function of prices and income, and it's simply equal to what we get by plugging the demand functions for x1 and x2 into the utility function we're using to measure utility for this consumer. Demand functions are functions of prices and income, and so what we're plugging into the utility function are two functions, x1 and x2, which are both functions of prices and income. This is why the indirect utility function ends up being a function of prices and income. What we're graphing here is a slice of the indirect utility function that holds the prices fixed and simply varies income. So suppose it is in fact true that any dollar in income results in an increase in utility of 0.25 as indicated in panel A by the slice of the indirect utility function that we've graphed. It must then be the case that if we want to give you enough money to increase your utility by 1 util, you'll need $4. In panel B, we're going to illustrate a slice of the expenditure function that holds prices fixed. The expenditure function here will measure how much in dollars we'll need to get to different levels of utility. So we put utility measured in utils on the horizontal axis and expenditures necessary to reach those utility levels on the vertical. If it's true that it takes $4 to buy 1 util worth of happiness, then it must be that this slice of the expenditure function has a slope of 4. It's no accident that the slope in panel B is the inverse of the slope in panel A. In panel A, this slope tells us for any additional dollar on the horizontal axis, how much additional utility we get on the vertical axis. So $1 buys 0.25 utils. In panel B, the slope tells us for any additional util on the horizontal axis, how much expenditure it takes to get that util on the vertical axis. If it takes $1 to buy a quarter util, it'll take $4 to buy 1 util, and 4 is therefore the slope in panel B. Just as the indirect utility function is a more complicated function than what we graph in panel A, the expenditure function is a more complicated function than what we graph in panel B. It tells us for a particular utility level U how much expenditures are necessary to reach that utility level. One way to determine that is to find the expenditure minimizing bundle to get to indifference curve U. That expenditure minimizing bundle is given by the compensated or Hicksian demand functions. So one way to derive the expenditure function is to derive first the Hicksian demand functions, which are functions of prices and utility levels, and then plug those into our expression for a budget, P1 times the compensated demand for 1, and P2 times the compensated demand for good 2. We can illustrate what's happening in both sides of our graph by using an example of a Cobb-Douglas utility function, x1 to the alpha, x2 to the 1 minus alpha. We can set up the utility maximization problem for a consumer with that utility function and derive the uncompensated demand functions for x1 and x2 which are given here as equation 10.7. It is those equations that we plug in for x1 and x2 in the Cobb-Douglas utility function to derive the indirect utility function given in equation 10.9. On the expenditure function side, we can start with this utility function and set up the expenditure minimization problem. Solving that problem, we find the least cost ways of reaching any given utility level U at any given set of prices. These are given by our compensated or Hicksian demand functions in equation 10.8. It is these that we plug back into our general expression for an expenditure function at the bottom to get the specific expenditure function for Cobb-Douglas preferences in equation 10.10. The slice of the expenditure function graphed in panel B is then an inverse of the slice of the indirect utility function graphed in panel A. In other words, we simply invert the axes to get from panel A to panel B. In panel A we measure the horizontal axis in dollars. In panel B we measure the vertical axis in dollars. In panel A we measure the vertical axis in utility terms, as we do for the horizontal axis in panel B. You can furthermore see how this works by simply inverting the V function in equation 10.9 by solving for I to get the expenditure function that's given in equation 10.10. Knowing how to get from an indirect utility function to an expenditure function or vice versa can be truly useful on an exam. You might be given one function or the other and then asked to derive a concept that you could easily get from the other if you can only get to it. It turns out it's pretty easy to get from one to the other. If you're given the indirect utility function, solve for I and replace V with U, and you get the expenditure function. If you're given the expenditure function, solve for U and replace E with I, and you get the indirect utility function. The fact that these are inverses of one another should also be relatively intuitive. The indirect utility function tells us for any given income how much utility we get. The expenditure function tells us how much income we need to get to different levels of utility. It's pretty easy to see, once you think about it, how one must be the inverse of the other.